right, down here in beautiful Palm Springs again. Different glasses, apparently. Raider shirt. Oh, yeah. Just win, baby. All right. Anyway, they didn't do that today, actually. They got killed by Atlanta. But anyway, let's take a look at our last section in chapter 4.4. We kind of go in a fun direction with this one as I look to share my screen here with you. Awesome. So this is really a real nice kind of more real world application of what we've been learning with lines. Okay, so let's go ahead and start with the warm up. Use the graph to write an equation of the line in slope-intercept form. Again, remember what slope-intercept form is? Go ahead and say it. You said y equals mx plus b, didn't you? Good. Awesome. Okay, go ahead and do that one. And obviously there were two different ways you could have done it. You could have done change in y's over the change in x coordinates, or you could have counted up and over. And either way, you would have gotten the slope was 8/3. Notice each box is worth 2, so be careful about that. And obviously the y-intercept is at 0,5, so it's 5, so it's y equals 8/3 x plus 5. Check it by plugging another point, including this point that we have right there. 8/3 times -3 would cancel the 3's and be a -8 plus 5. Does that equal the -3 that we plugged in for the y? Absolutely. Okay, next one, graph the linear equation y equals x minus 5, and then identify the x-intercept. And remember, there's two ways of finding the x-intercept. Okay, so hopefully you just went to the y-intercept of -5 because it was in what form? Oh yeah, y equals mx plus b form. Slope's what? 1, which means rise 1, run 1. So up 1 over 1, or down 1 to the left 1, however you want to do it. And we'd have this line. What's the x-intercepts? It looks like it crosses right at 5. How could we check that? You could plug in what? 0 for y, and then solve for x. And if you plugged in 0 for y and solve for x, you'd add 5 to both sides and you get x equals 5. Awesome. Okay. Our learning target here is to be able to use a scatter plot and a line of fit to make conclusions about data. Okay. I love this lesson. I think this is really a good one, and you'll see this in pretty much almost anything you go into. You'll be dealing with lots of data on graphs and so forth. Okay, so you can work with your invisible partner again, or call a friend, or someone at home. A survey was taken of 179 married couples. Each person was asked his or her age. The scatter plot shows the results. So you can see the results over here. So always important, again, when you're looking at a graph, what's it all about? Ages of married couples. Okay, what are the axes representing? Husband's age, wife's age. And notice what they did here. Notice how they kind of made like a little break in the graph and said, okay, yeah, 0, 0 is right down here at the origin, but we're quickly jumping up to 30. So that first box is not the same as each other box is 5. Okay, so you have to be careful when you see something like that. Just make sure you recognize it. Okay, so draw a line that you think best represents the data. Okay, and then write an equation of your line in slope-intercept form, and then explain how you got there. Like how did you decide to draw the line that you drew? Go ahead and give it a shot. Let's see what you come up with. So what I did was I drew mine that went basically kind of through the data as much as possible. So you see I have my line, what we call a line of best fit, even though it's really kind of array, has most of the data is real close to it and some on both sides. Okay. So, and then if I wanted to figure out what my equation was, well, what's my y-intercept? Looks like it's pretty much down at 0. And what's my slope? Looks like I'm going up 5 for every 5 that I go over. So it would be y equals x, right? Okay, so what I did was I graphed the line through what looked like the middle of the data, talked about that. I noticed that the rise of the run is the same between any 2 points on the line, so the slope's 1. Okay, so what conclusions can you make about this situation of married couples? What would you say based on that? So it says the age, each half of a married couple is about the same. Okay, that's basically what it shows. So it's showing that in general, married couples are about the same age. Not always, certainly not always, but pretty darn close. Like, for example, I'm a good example of that. I'm 9 months older than my wife, 8.5 months actually. So anyway, all right. So here's another scatter plot. Here's a thing that says that shows the median age of American women at their first marriage for selected years from 1960 through 2010. So this is not a study or whatever research that goes before 1960, and it doesn't go after 2010. So what's the first year? 1960. So we're using that as year 0. Again, analyze the graph. So what do we have? We have about ages of American women at first marriage, the year of the marriage, and the age of the woman. Okay. So what would your line look like? Hopefully something like that, right? Notice again, it's real close to most of the data points. There's some that are below, there's some that are like on or slightly above it. So again, I use my line of best fit to estimate the slope. Okay. And what is that? Well, slope is about 0.1. And notice, like if I pick this point, which is kind of almost at 0.20, it's really like 20.1 maybe, I don't know. And I pick this point right up here at 1990-24. That's what? A rise of 4, a run of 30. So, you know, that's approximately 0.1, maybe not quite, but again, this is kind of approximating things, right? So what is this saying? This is saying the median age of women first marrying increases by 1 year every 10 years. So in other words, in 1960, when a woman got married for the first time, she was just barely over 20 years old. But if you go out to 1970, all of a sudden it's closer to 21. It's a little less than that. But then if you go out, you know, all the way to 1990, it's a little bit above that line. Okay. So what's great about this is once you have a line of best fit, you can make predictions. So on part C here, we're going to say, use your equation to predict the median age for American women with their first marriage in the year 2020 this year. What do you think it would be? Yeah, you could go over here and look at your line of fit, right? And do it this way. Looks like that would be what, about 27? Or since they said use the equation, couldn't we plug in for the number of years? What year is 2020 if 0 is 1960? It's year 60, right? So we could actually plug in 60 for X, and then let's see how close I was. Okay, so yeah, 26. So it's a little over 26. And what do we say? We said 27. So pretty close. Okay. All right, so what is a scatter plot? Well, the core concept here is a scatter plot is a graph that shows the relationship between two data sets, right? We saw that between the age of a man or two people getting married, right? We saw 2 data sets, the year, and we saw how old a woman was when she first got married, okay? The 2 data sets are graphed as ordered pairs in a coordinate plane. We saw that. Scatter plots can show trends in the data. Sometimes, not always, and we'll see that. Okay, so the scatter plot here shows the amount X in grams of sugar and the number Y of calories in 10 smoothies, okay? So notice how there's 10 dots here, 4, 5, 6, 7, 8, 9, 10, right? And the x-axis represents the number of grams of sugar, y-axis the calories, okay? So if you were asked to answer the question A, how many calories are in the smoothie that contains 56 grams of sugar, you would need to do what? You need to go find the one that had 56 grams of sugar by looking along the x-axis. Oh, that one does. How many calories are in it? Oh, 270. Try B. How many grams of sugar are in the smoothie that contains 320 calories? Okay, so here we're not we don't know the number of sugar. We're trying to figure that out. We know the number of calories. Go up to 320. It's the only point that's there. 70 grams. Okay, so what tends to happen to the number of calories as the number of grams of sugar increases? What do you think? Hopefully you said that the number of calories increases also, right? If we drew in a line of best fit, it would kind of be something like that goes along that, right? Alrighty. Okay, so here it is again. Another question. How many calories are in the smoothie that contains 51 grams of sugar? You said 260. And how many grams of sugar in the smoothie contains 250 calories? Very good. Yes. 250. That's that one there. That's about 52. Okay. So a correlation is a relationship between data sets. And we already said a scatter plot is two different data sets, right? So you can use the scatter plot to determine the correlation between data. Here's what we call a positive correlation. As your x coordinate, your x values increase, what happens to the y's? They also increase. Goes up to the right. What else do we know has a positive something that goes up to a right? Oh, a line that goes up to the right is a positive what? Positive slope. Same thing with correlation. Negative correlation. As x decreases, as x increases, in other words, as we move points further out here, what happens to the y values of those points? They go down. That's a negative correlation, just like a line that goes down to the right has a negative slope. And this, there's no pattern there. That does nothing for us. No correlation at all. Okay, so analyze this graph here on the left, age and vehicles owned. And tell me whether you think it is a positive, negative, or no correlation. Okay, yeah, pretty much no correlation there, right? Nothing that indicates that, at all. Okay, what about temperature and coat sales at a store? It's a negative correlation, right? As it gets colder, what do you think happens to the number of sales? They go up, right? All right, awesome. Okay, so here, I want you to make a scatter plot of the data. You're told that the temperature in Fahrenheit is your X value. The attendees in thousands of people is your Y. Make a scatter plot of the data, and then let's determine whether it's positive, negative, or no correlation. So you should have 8 points on your graph when you finish. Go ahead and pause, do it, and then tell me what you think your correlation is, if there is one. Okay, so there's the plotting. Yeah, it definitely looks like a positive one. If we drew a line of best fit, it might be something that goes kind of like that. And that is definitely positive. All right, do this one. Same instructions. Age of a car in years, its values in thousands of dollars. Okay, so hopefully when you plotted those 8 points, they look something like that. And that clearly is a negative correlation, which makes sense, right? You would think that as a car gets older, it goes down in value. What's interesting, though, is that once you hit a certain time, and something can become even more value as it gets older. My dad has it's older than me. I think it's a 1965 or 1966 Porsche kind of little coupe. And for a long time, it went down in value, and then it started to go up, and now it's worth a ton of money. So interesting how those things happen. Maybe I should hold on to my Tiguan that barely runs. Nah, it's only a 2010, and yeah, it would be way too long to make that a collector's item. Probably 50 more years. All right, so. Whoa, there goes the laundry off kilter, but that's okay. So using a line of fit to model data. This is nothing that this is just kind of a summary of what we just went through. Make a scatter plot of the data, right? Plot your points. Step 2, decide whether data can be modeled by a line, right? If it's a positive or negative correlation, it means you can draw in a line that appears to fit the data closely. We call that the line of best fit. Remember that. Learn it. Love it. Okay. Ooh, there goes the sound again. There should be approximately as many points above the line as below it. And that's approximate. Okay. And then step 4, write an equation using 2 points on the line, right? The points do not have to represent actual data pairs, but must lie on the line of fit, right? So in other words, once we've plotted, like if we went on here, after we plotted the data points, let me actually use a line. And yeah, let's just go like, boy, let's see if I can do this pretty well. Boom. Like, let's say this was your line of fit, right? So I have some that were above, some that were below, something like that, right? Well, what you can now do is you can graph, we just graphed it, right? But we can write an equation by picking 2 points that we feel are on the graph. Whether they're actually the points that were plotted before or not really doesn't matter. So for example, here, I could say, oh, okay, I think that's like 0, 25, and that one right there is 7, 10, right? So I could go 0, 25, and what did I say? 7, 10, right? And we could actually use these 2 points, right? We could go 25 minus 10, right? This is, remember, parentheses. 25 minus 10, that would be 15. That's our change in our y's over our change in our x's, 0 minus 7, which should be -7, which means our slope is -7, right? So what would the equation be? Y equals -15 over 7x, and then what? What would come next? I think I said 0, 25, right? So plus 25. Okay, so that would be a way of using 2 points that are on your graph, just like we did before. Okay. All right, so here we have a problem where it shows the weekly sales of a DVD and the number of weeks since its release, okay? Write an equation that models the DVD sales as a function of the number of weeks since its release, okay? Interpret the slope and y-intercept of the data, of the line of fit, excuse me. Okay, so here we go, right? We've got the points plotted. We did that. That was step 1. Then we drew our line of best fit. Notice how there's points on both sides, approximately the same number. And now we need to write an equation that models this, right? So we could pick 2 points, right, that are on our line of fit. I'm not asking you to do this data. This is non-linear, right? It doesn't line up. Increase of 1, decrease of 4. Increase of 1, decrease of 2. It's different. It's not, we're doing it for the line, okay? So let's pick 2 points that are on our line. So I did, let's see, 5, 10, oh yeah, they're labeled here, and 6, 8, right? Those are on our line of fit. And so I did 8 minus 10 over 6 minus 5, which gets me -2 over 1, which is -2. And now I can substitute m and the coordinates of any point into point slope. So for whatever reason, I decided to use 6, 8, okay? So what formula is that again? Point slope, say it to yourself. Hopefully you said y minus y1 equals m times quantity x minus x sub 1. So 8 goes in for y minus, that's the y sub 1, right? 6 goes in for the x sub 1, and our slope was -2. And then we can put it into slope-intercept form, distributed, right? So -2x plus 12. And then what am I going to do? I'm going to add 8, and boom, there's our equation. So what does that mean? What does the slope say in terms of this? What does it say? Okay. The sales are decreasing by about 2 million each week, right? And on average, that's about what it is, right? And the y-intercept Now you would think, oh, it means the first week they sold 20. No, no, no. First week they sold 19, right? See that? That's right there. This really has no meaning, right? Because you don't sell in week 0. You sell the first week. Okay. All right. I think that was it. It is. How about that? Okay. So that's it for chapter 4. Congratulations on finishing that, and we'll do a little test on it and hopefully do real well, and then we'll move on into chapter 5. All right. See you soon.